All right. So we've talked about the basics of free body diagrams and putting that stuff into Newton's second law. Now we're going to talk about some kind of specific cases and how to approach them. So here are a few specific cases for Newton's second law. The first one is when you have collections of bodies in contact. That have the same acceleration. So we're just going to talk about kind of like when you see stuff like that, how to approach it. The second thing we're going to talk about is rolling and sliding problems. We've already seen some like this, but we're going to do it when the surface is not horizontal and talk about how to approach that. And then the last one is collections of bodies connected by cables and pulleys. And the thing, when you have pulleys in these problems, what it does is change the direction of the force and change the direction of the acceleration. So this is the case where these connected bodies have different accelerations. Okay, like you can imagine if you have an object hanging from a cable, goes over a pulley, and then it connects to another object on the other end. If one accelerates up, the other one has to accelerate down. So that's a case where they have different accelerations, and that's what that'll be. And it's the pulley that makes that possible. Okay, so the first one, we're going to talk about collections of bodies in contact. That have the same acceleration. And first, I'm just going to tell you the approach, and then I'll show you sort of how that looks as you do it. So the overall approach is, instead of isolating the individual bodies to start with, you isolate the whole system as if it's a single thing. You can always isolate collections of things. You know, we've seen free body diagrams of like a person or something. Well, there's lots of stuff. Your body has lots of stuff in it. I don't know if any of you are aware of that, but there's like all this stuff in there. And so really, if your free body, the thing you're isolating is like a human body, you're really lumping a bunch of stuff together, you know, millions, billions cells or whatever, and all this stuff and blood going here and whatever. You can always choose as your free body a collection of things. So first you're going to start by isolating, so isolate the entire system. And solve for the acceleration. And just to be clear, the acceleration vector. So we're going to get that acceleration vector. Once you've calculated the acceleration, then go back and isolate individual bodies. And use the acceleration that you just calculated. So use that acceleration vector in Newton's second law. Okay, so here's an example. Let's say that you have two rolling carts in contact with each other. This one's 5 kilograms, and this one's 10 kilograms. And there's a 25 Newton force being applied to the side of the 10 kilogram one. And we want to know, so calculate the force vector applied to the 5 kilogram by the 10 kilogram. Okay, so let me sort of describe why it wouldn't work. I mean, if we're trying to calculate a force on the 5 kilogram mass, why not just isolate the 5 kilogram mass and then just directly calculate that force? Well, think about the horizontal stuff going on if we isolate that 5 kilogram cart, okay? There's a pushing force on it from the 10 kilogram, okay? That's horizontal. So that's one horizontal variable. And then the acceleration is also horizontal, so that's a second horizontal variable. And we only have one horizontal equation, the x equation from Newton's second law, so you can't calculate two variables with that. But if we isolate the whole thing, remember that the contact forces you include are just when the surroundings touch the boundary. And so those the contact forces between those bodies disappear from the analysis. They're not happening on the boundary anymore. And so that isolating the whole thing lets us calculate the acceleration. Then we can go back and use that to calculate other unknowns. So you don't have to, if you have extra time and feel like it sometime, try one of these and you'll see how it happens that you end up with more variables than you have equations and there's nothing you can do. And that's what makes it useful to isolate the whole system. So, okay, free body diagram of the whole system. You don't have to turn this into like an art class, but that's what we're isolating, the two carts as if they're a single thing. There's a weight force acting down. The mass of the whole system is 15 kilograms. So 15 times 9.81 is 147.15. There's a 25 Newton force acting over here. And the only other place the surroundings contact this boundary is the pushing force from the ground. So I'll call that N total, which is just a variable name, I use those subscripts so I can call different things N's and still have them be different variables. And now go to Newton's second law. We have the downward force of 0, negative 147.15. We have the pushing force from the ground that's in the positive y direction. So this is 0 N total. The 25 Newton force is in the negative x direction, so this is plus negative 25, 0. And then that's equal to the mass of what we're isolating, 15 kilograms, times the acceleration vector. And with the acceleration vector, you always have to ask yourself, is this thing going to move along the x-axis or the y-axis? In this case, x. So I'm going to write this as a0. Okay, well, two equations come out of this, an x equation and a y equation. The x equation says 0 plus 0 minus 25 is equal to 15a. And the y equation says negative 147.15 plus n total plus 0 is equal to 15 times 0, so 0. And now ask yourself, which of these two things, which of these two equations gives us what we're trying to solve for? Well, notice that this is the acceleration vector, right? The reason we're isolating both of these is to calculate the acceleration vector, and that's what it is. We just don't know what a is yet. So we're going to use the equation that lets us find that variable a, okay? The y equation would let us calculate n total if we wanted it, but that's not what we're looking for here. So I'm going to use this x equation to find a. So that equation says negative 25 is equal to 15a. And so a is equal to 1.6 repeating meters per second squared. Now plug that into the acceleration vector that we used here in Newton's second law. And you get that the acceleration vector is, oh, I left off a negative. Nope, not there. Here. Okay, a is equal to negative 1.6 repeating. So plug that into the vector and you get negative 1.6 repeating and then 0 for y. And that's meters per second squared. And if you want to visualize that, that's in the negative x direction, which is this way, with a magnitude of 1.6 repeating meters per second squared. So this whole thing is accelerating to the left. Now that we have that, now we can isolate the 5 kilogram. So now I'm going to draw a free body diagram of the 5. There's a weight force of 5 times 9.81, so 49.05. And now the contact forces. There's a pushing force from the ground. I'll call that N5. And there's also a pushing force from the 10. I'll call that R. And so now Newton's second law says 0, negative 49.05 plus 0 N5 plus this R force is in the negative x direction, so negative R, 0. And that's equal to the mass, 5, times the acceleration vector we just calculated because everything is accelerating the same. So this is negative 1.6 repeating for x, 0 for y. And we're trying to calculate the force vector on the 5 by the 10. So we're trying to calculate this. Okay. So you get two equations out of this. The x equation says 0 plus 0 minus r is equal to 5 times negative 1.6 repeating is negative 8.3 repeating. And then the y equation says negative 49.05 plus n5 plus 0 is equal to 5 times 0. Okay, well, if we're trying to calculate that force vector that's in that dotted circle, which of these two equations is useful to us? The x equation, yeah, because all we're trying to find is that variable r. Okay, so again, I'm going to use this one. So we have negative r is equal to negative 8.3 repeating. And so r is equal to 8.3 repeating. Since everything we're doing is in SI units, this is newtons. Now that we have that variable, all we have to do is plug it into the force vector from Newton's second law. So the force on the 5 by the 10, that's this thing, the one in the red circle. That is equal to, so we got a variable value that's positive, but now plug that into r here, and there's a negative sign we have to add onto it. So we get this vector of negative 8.3 repeating 0 for y. Or in other words, it's in the negative x direction with a magnitude of 8.3 repeating newtons. And this is a really useful thing to be able to do for engineering applications because, you know, if you're doing this for something that's part of a machine or, you know, some kind of application, I mean, normally the way this would be used in an engineering application is you want to make the materials that are experiencing this force strong enough to deal with that force, but you don't want to overbuild them where you're spending extra money on materials you don't need, you know. And so based on this, we know that in this application, we need those walls to be thick enough to deal with an 8.3 Newton force. Okay, so that's it for this example. But what if instead of isolating the 5 kilogram cart, we isolated the 10 kilogram cart? It seems like a weird choice to make, but could we get the same answer? Yes, we can. And I want to show you that you can do that because in some cases, that's the better way to go. Okay, and we'll get to some examples like that. So we could have gotten the same answer by isolating the 10 kilogram instead of the 5. So say we already did the part where we isolated the two things together, we calculated the acceleration. And now instead, let's isolate the 10 kilogram and see what it looks like. So free body diagram of the 10. There's a weight force of 10 times 9.81, so 98.1. Go all the way back up to the picture. There's this 25 Newton force on the right side. There's a pushing force from the ground here. I'll call that N10. And then the last thing we have to put in is the 5 now is pushing on the 10. Okay, so that's perpendicular to the surface toward the chosen body. And I'll call that R. We're pretending we didn't already calculate R, you know. So that's it. So now we go to Newton's second law. We have this R in the positive x direction. We have the weight. We have the pushing force from the ground in the positive y direction. We have the 25 in the negative x direction. And that's equal to the mass times the acceleration that, you know, we already calculated. And this force here is the force on the 10 by the 5. So break this into the two equations. It says R plus 0 minus 25 is equal to negative 16.6 repeating. And the y equation says 0 minus 98.1 plus n10 plus 0 is equal to 10 times 0. Which of these two equations is useful for calculating the one in the red circle? Yep, it's x again. So that says R minus 25 is equal to negative 16.6 repeating. Solve for R, and you get R is equal to 8.3 repeating newtons. And so this says that the force on the 10 by the 5 is equal to, plug it into this force vector, and you get 8.3 repeating, 0 for y, or in other words, a vector in the positive x direction with a magnitude of 8.3 repeating. Okay, well, that's the force on the 10 by the 5. But we know that when we're going between two bodies that are in contact, the force they feel has the same magnitude. We use that same variable. The only thing that changes is the direction is opposite. So for contact between two bodies, the force on the 5 by the 10 in this case is the negative of the force on the 10 by the 5. And so you get negative 8.3 repeating 0. Or just what we got before. So we could have done that either of those two ways. The thing that's surprising about that, does anyone have any questions before I keep going? The thing that's surprising about that is, notice that when we isolated the 5 kilogram thing, there was nowhere on here where we said anything about that 25 Newton force. When we isolated the 10, that 25 Newton force is there. So it's like, in that first case, how does it know that that 25 Newton force is happening? How did we get the same answer with those two approaches? Yes, that's exactly right. So in that first step where we found the acceleration, that 25 Newton force is sort of baked into the answer. Okay? And so then when we use that acceleration later, it was all, that information is already in there. Okay? Anybody have any questions about that? Okay, let's do another one. So let's say we have 3 rolling carts connected by cables. Let's say this is 1 kilogram, 2 kilograms, and 3 kilograms. And then we'll apply a 30 Newton force this way. And let's say we want to find the force vector applied to the 2 kilogram cart by that left cable. So the cable that's holding the 1 and the 2 together. So I'll start with a free body diagram of the whole system. Whoop. You don't have to do this carefully. I'm just trying to make it clear what I'm looking at. So there's the system. It has a total of 6 kilograms of mass. So there's a downward force of 6 times 9.81. So 50, I think that's 58.67, is that right? Okay, 58.86. And then what else is acting? There's a 30 Newton force over here. And a pushing force from the ground, that's right. So I'll call that N total. So Newton's second law says 0, negative 58.86 plus 0 N total plus 30 0 is equal to 6 times the acceleration. Is this thing moving along the x-axis or the y-axis? X. So I'll write this as A0. And I get two equations. The x equation says 0 plus 0 plus 30 is equal to 6a. The y equation says negative 58.86 plus n total plus 0 is equal to 0. To calculate the acceleration, I want the x equation. And so that says 30 is equal to 6a, and so a is equal to 5 meters per second squared. And then put that in the acceleration vector, and you get 5, 0, which if you're trying to interpret what's going on, that's an acceleration in the positive x direction with a magnitude of 5 meters per second squared. Okay, so now what do you want to isolate? We're trying to calculate the force vector applied by one of the cables to the 2 kilogram cart. Okay, well, if we isolate just the 2 kilogram cart, which is the first thing that would probably occur to you, there's an unknown horizontal force, pulling force one way, and another unknown horizontal force going the other way. So we can't in one step do it with the 2 kilogram cart. Okay, there are two ways that we can do it. We can isolate the 1 kilogram cart, calculate the cable force on that, and then recognize that that same cable applies the same magnitude of force in the opposite direction to the 2. So that's a good way to do it. The other thing we could do is isolate the 2 and the 3 together as a single thing, and then we'll see that cable force will be the only horizontal force in this system, because the cable force between the 2 and the 3 then is internal and it doesn't show up in the free body diagram. And those will give the same answer. Okay, so I'm going to do the 2 and the 3 together. All right, so there's a weight force down. The mass of this whole system is 5, so this is 49.05. There is a 30 Newton force pulling over here. There's a pushing force from the ground. I'll call that N23. And then the last place the surroundings make contact with the boundary is the cable over here. And so that force is parallel to the cable, away from the body, and I'll call it T. And then Newton's second law says that T force is in the negative x direction, so negative T0 plus 0, negative 49.05 plus 0, N23 plus 30, 0 is equal to the mass, 5, times the acceleration, which is 5, 0. And this is the force we're trying to calculate, so all we need is that variable t. The x equation says negative t plus 0 plus 0 plus 30 is equal to 25. The y equation says 0 minus 49.05 plus N23 plus 0 is equal to 0. And we'll use this equation to calculate t. Negative t plus 30 is equal to 25. So negative t is equal to, subtract 30 from both sides, you get negative 5. So t is equal to 5 newtons. And if you plug that value for t back into this force vector, you get that the force on the 2 kilogram by the left cable you have a positive value of 5, you plug it into this vector with a negative, and you get negative 5, 0 newtons, or a vector in the negative x direction with a magnitude of 5 newtons. So I'm not going to go through this calculation, but think about it for a second. So now what if I had isolated the whole thing, calculated the acceleration vector as a first step, and then isolated the 1 kilogram cart over there on the left, okay? Then we would be able to calculate the cable tension, the cable force that left cable applies to the 1 kilogram cart. What direction would that force be in? It would be in the positive x direction with a magnitude of 5. And then we would know that if we want the force that cable applies to the 2 kilogram cart, the direction would be switched. So we could have gotten the exact same answer that way. Okay? Okay, let's do one with some vertical stuff going on. So, okay, let's say that there is, at the circus, there's this teeter-totter. And this elephant stands on it. I'm great at drawing elephants. That's why I'm doing this. Uh-oh. I think it's going wrong. Come on. Oh, I think it's coming back together. Yes. Okay, so that elephant stands on the teeter-totter. And then on the other side of the teeter-totter, you have the circus performers. And let's say it's two guys, one standing on the other one's shoulders. This is pretty common circus type stuff. If you've ever been to a circus, you know. Okay, so this elephant is going to launch these guys up into the air. But we're going to do some calculations about what kind of forces these people are going to need to withstand in order for this to happen. Okay, so let's say that the teeter-totter pushes up on the feet of the bottom guy with a force of 3,000 newtons. Okay, and let's say that this bottom guy has a mass of 100 kilograms, and the top guy has a mass of 60 kilograms. And let's say that the top guy doesn't have very good knees. Okay, so we want to calculate what kind of force he's going to have to. That happens in circuses all the time. I used to be in the circus industry. I know this stuff. Not really. Yeah, exactly. I was a clown. So we want to calculate the force that the shoulders of the bottom guy applies to the top guy's feet. Okay, to see if his knee can withstand this. So what's the force vector applied to the top guy's feet by the bottom guy's shoulders? All right, so the first thing we're going to do is isolate both of these two guys together as a single thing. So free body diagram of both of them. There's a weight force down. Their total mass is 160. So actually, can someone calculate that for me? 160 times 9.81.
1,560.6.
569.6?
Yeah.
Okay. Okay, so that's the weight force. There's a force pushing up on the bottom guy's feet, and we're given that that's 3,000 newtons. And there are no other places where the surroundings contact the boundary. So now we'll go to Newton's second law. Oh. Sorry. So Newton's second law says 0, negative 1569.6 plus 0, 3,000 is equal to the mass of the system, 160, times the acceleration vector. Is this pair of people going to move along the x-axis or the y-axis? Y. So this is 0, A. And so we have an x equation that clearly doesn't give you any information, just 0 plus 0 equals 0. And then a y equation that says negative 1569.6 plus 3,000 is equal to 160 times A. We're trying to figure out the acceleration vector from this. So we're going to use this equation. So you get 1430.4, is that right?
Yeah.
1430.4 is equal to 160A. And so divide 1430.4 by 160. Could you do that for me? 8.94 meters per second squared. Plug that back into the acceleration vector, and you get an acceleration vector of 0, 8.94. Or, they're going to accelerate up at 8.94. And now we can really get this information by isolating either one of these two guys. The more direct way is just to isolate the top one. The only time we wouldn't do that is if there are going to be additional force variables that are going to keep us from solving it that way. So let's just isolate the top guy. So free body diagram of the top guy. There's a weight force down of 60 times 9.81. So that's 588.6. And then there's a pushing force from the shoulders. And the rules of a pushing force are perpendicular to the surface, the feet, toward the chosen body. So it has to be that way. And I'll call that R. And that's a complete free body diagram. So now Newton's second law says 0, negative 588.6 plus 0, positive R is equal to the mass, 60 kilograms, times the acceleration that we just calculated, 8.94. So you get one useless equation, and then one useful equation, negative 588.6 plus R is equal to, what's 60 times 8.94? 536.4. And so using that equation, let's see, you get R is equal to 536.4 plus 588.6. 1,000, oh, I lost it. Can you add that for me?
1,125.
1,125 newtons. Well, this is the force vector we want. So now plug the value in there. And that says that the force on the feet by the shoulders is 0, positive 1125 newtons. So in order to perform this maneuver, the legs of the top guy need to be able to withstand an upward force of 1125, which is about a little over 250, maybe 260 or so pounds of force, which seems reasonable, you know. Anybody have any questions about that? Okay. Let me write one up here, and I'll give you time to go through it, and then I'll go through it and just make sure you're sort of following the steps. So let's say this is 50 kilograms. This is 100 kilograms. And there's a force pushing to the right of 200 newtons and a force pushing to the left of 300 newtons. What's the force vector on the 100 by the 50? Okay, so the first step is to isolate both of them together. So I'll pause this, take a few minutes, isolate the whole system as a single thing, and see if you can calculate that acceleration vector. Okay, then I'll go through that step, and then I'll give you some time to do the second step. Okay, so isolate the whole thing. And before I get into this, remember that the benefit of doing this kind of stuff is if there's a place where something you do wasn't right, you can identify the part of this that you misunderstood something, okay? So please, pay attention to if there's anywhere where this is different than what you did. We have a weight force of 150 times 9.81, that's 1471.5. We have the 300 here and the 200 here. A pushing force from the ground. I'll call that N total. You can call it whatever you want. So Newton's second law says positive 200, 0, plus 0, negative 1471.5, 0, positive N total, plus negative 300, 0, is equal to the total mass times the acceleration. This thing is moving in the horizontal direction, so the acceleration is a0. So the x equation says 200 plus 0 minus 300 is equal to 150a. The y equation says 0 minus 1471.5 plus n total plus 0 is equal to 0. The x equation is the useful one. And so we get negative 100 is equal to 150a. So a is equal to negative 0.6 repeating. That's meters per second squared. And so if you plug that back into the acceleration vector, you get negative 0.6 repeating, 0 for y. And if you're trying to visualize it, that's an acceleration this way with a magnitude of 0.6 repeating. Okay, any questions about that? Yeah.
At the beginning, I did just the 300 newton minus the 200 and put in the second law just negative 100.
Yeah, that's fine. Sure. Yep. Later on, when we start talking about changing orientations of rigid bodies, like here's the thing. Right now, we're treating everything like particles. Later on, you'll only be able to do that if they act at exactly the same point. But for now, that gives the same answer for everything. So yeah. Any other questions? Okay, so now we're going to isolate. We're trying to calculate the force on the 100 by the 50. So let's isolate the 100. Okay, so I'll turn this off. Take a couple minutes and see if you can calculate the force on the 100 by the 50. Okay, so I'm going to isolate the 100 kilogram. There's a weight force down of 100 times 9.81, so 981 newtons. There's a 300 Newton force over here pushing to the left. There's a pushing force over here from the 50. That's the force vector we're trying to calculate. And then there's a pushing force from the ground that I'll call N100. And then Newton's second law, you have positive R0, negative 300, 0, plus 0, negative 981, plus 0, N100, is equal to the mass of 100 times the acceleration vector, negative 0.6 repeating, 0. The x equation says r minus 300 plus 0 is equal to 66.6 repeating, negative. The y equation says 0 plus 0 minus 981 plus N100 is equal to 0. This is the force vector we're trying to calculate, so we want that R value. And so the X equation says R minus 300 is equal to negative 66.6 repeating. So R is equal to positive 233.3 repeating newtons. And now to get the force vector, you can just plug it back into this vector here and you get 233.3 repeating 0, or a vector in the positive x direction with a magnitude of 233.3 repeating newtons. Any questions about that? So the total, to make sense out of that, the total force pushing on the whole system is just 100 going to the left, right? But the contact force between those two is bigger than that because you have the two forces smushing them together. Okay? All right, that's it. Have a good weekend.